So I hope my slide is visible with perforated area in PPT mode. Yes.
Yes, ma'am.
Okay. Thank you. So before starting today's class, let me revise the content which we have covered in the last class. So in the last class, we have discussed each step uh, which is required to complete the design of distillation column. A day before yesterday, we have seen different steps which are involved in plate design. And from yesterday class, we have started exploring each step. Okay, so we have seen how to find out the diameter, then liquid flow pattern, and apart from that, different areas and what is net area, what is that perforated area and all. And we have seen that how to decide the hole pitch, weir height and weir length. Okay, depending upon the downcomer percentage. And downcomer percentage is also an important parameter to discuss, and which varies from 12 to 15 or so. Okay, so all that we have discussed, and we have also seen how to decide the how to decide the whole pitch. And that whole pitch is basically distance between two uh, center to center distance between two consecutive holes, right? So that we have discussed. And apart from that, we have seen the condition, okay, where all these parameters will be um, what we can say feasible. Okay, so that we have discussed. And we have also covered this perforated area, different angles and all, that we have discussed in the last class. So your active area minus perforated area is basically the uh, active area minus calming zone is equal to perforated area, that we have discussed yesterday. So let's continue with this. There are many more parameters to calculate, and then we used to bring those parameter in visible range, right? So let's start today's content. So today we will start with plate pressure drop. Okay. So plate pressure drop, when I'm considering, it means how much pressure uh, will be there when I'm considering a single plate. Okay. Uh, Apart from all, like apart from distillation column, sorry, apart from diameter of the column, we have all parameters which we used to calculate for location wise. Otherwise, uh, the column diameter should be calculated for both the location above feed and below feed, and then higher one we can choose. Okay, all these will be more clear when we will solve a few examples. Okay, we discuss the few examples. So the plate pressure drop, when I'm considering, it means how much pressure drop is there over the plate, and it will depend on the geometry of the plate. It will depend on the flow which is passing through the plate. Okay, so let me discuss that plate pressure drop, and what are the different elements of this to consider. So when we consider the sources of pressure loss, because pressure drop, when I'm saying, that should be connected with the frictional loss, right? So there are two main sources of pressure drop, that due to vapor flow through the holes. Okay, when a vapor is flowing through the holes, it depends on, it will create certain frictional loss. Okay, so that because of the vapor flow rate. And when we consider the vapor flow rate pressure drop, we do not consider the liquid, because liquid we are considering entirely, considering in different way. Okay, so what I'm saying, that when we consider the vapor flow through the holes, we consider the dry plate condition. okay, where liquid is not available. Okay, so we need to find out pressure drop for each section, and then we will add to find the total, right? So the main sources of pressure drop is vapor, which is passing through the hole, and that we consider as dry plate. Okay, dry plate condition. And secondly, that is due to the static head of the liquid over the plate. So static head of the liquid plus the what we can say, friction loss by vapor when it is passing through the hole, and that we count as dry condition. Okay, so total pressure drop when I'm considering, that is flow which is equal to flow of vapor through dry plate. Okay, the dry plate drop, that is hd, we represent that hd. Okay, dry plate, you understand na, that we do not have any liquid so far. Okay, liquid we are counting in different way, like head of the clear liquid on the plate, that is hw. Hw is the wear height that we have discussed in many classes before. So HW is the wear height and HOW is the crest height. How much layer of liquid is available over the wear? Okay, so these two will give the total head. Okay, and which we call as the static head. And further, we have some residual losses. Okay, so that we represent as HR. Now, see the expression for pressure drop in the plate. So that pressure drop will nothing but rho g h. Okay. And this ht is in mm, therefore 10⁻³ is there. Otherwise, that is nothing but rho g h t. Okay. So ht we need to consider. So ht will give total head on the plate, and that is in mm. Okay, mm liquid. So we will see how to find this HD, HOW, W that you already have fixed before. Okay. So dry plate pressure drop when I'm considering, when you consider a hole over the plate, okay, or what we can say, when a hole is made in the plate, right? So that is the small hole through which vapor is moving. Okay, so that we can resemble with the orifice meter, because orifice meter also has a smaller hole through which liquid or fluid passes through, and we consider the pressure drop by putting manometer to both the side, before the hole and after the hole. Okay, so we will consider the same uh, condition over here, that dry plate when vapor is passing through a small hole, that we can represent, that we can resemble with orifice meter. Okay, so orifice meter calculations or coefficient we can use over here. I hope you are able to understand. Okay, so when I'm considering dry plate pressure drop, that is related with this equation, where I'm having this rho v and rho l are the, what we can say, rho v and rho l are the ratios of vapor and liquid. CO is the orifice constant, and UH is the vapor velocity through hole. Okay. So vapor velocity through hole means whatever location you are considering, for that you already know the vapor flow. Right? And that we will vapor volumetric flow, and that we will divide with the whole area. Okay, this is UH is nothing but the whole area, and whole area when I'm considering, this is not a single hole, this is for all holes available in the plate. Okay, so like yesterday we have discussed that whole area to active area, that may be 8% and 9%, 10% like that. Okay, so based on that, we find out this UH, and then HD we can calculate once I know CO. So how much CO we can have, like here I'm having percent floor perforated area. Okay, so this is nothing but AH by AP. AH is the whole area divided by AP. Okay, it shows that how much area of perforation section, perforation area, how much area from that is dedicated to whole area. Okay, so therefore it is AH by AP, and I'm having different lines, and this lines, all these lines show the plate thickness by hole diameter, as you can see over here. Okay, plate thickness that we have seen how to decide. Okay, 3 mm, 5 mm, like that we need to consider. Hole diameter you have already decided, like it varies from 2.5 to 12 mm, but 5 mm is the recommended value to start with, right? So plate thickness by hole diameter you can calculate, and uh, you can find out CO from here. AH you have already you are already aware of, and AP you have already calculated. So with this we can find HD. Okay, please let me know if you have any confusion. Uh, HD is the dry plate head, and once I'm having this HD, we will find out the residual head, because HW, HOW that you have already decided earlier. Okay, so nothing more to be decided for that, to calculate that. Uh, Only we need to find out residual head. Okay, so this residual head is very like very simple to calculate, like 12.5 times power 3 by rho L. And this residual loss, like minor losses, major we have already covered in HD, HW, or and HOW, but residual losses are there, that may be because of the interaction between vapor and liquid and like that. Okay, so based on that we can we can find out this HR. Once I'm having the HR, we can find out total head over the plate, and that we represent by HT, which is equal to HD plus HW plus HOW plus HR. Okay, so based on that, we can calculate, and then pressure drop, we have already seen rho g HT, that you can calculate. But all these values are in mm. Please keep in mind. Just a moment, please. Yes. So in this way, we can find out the total pressure drop over the plate. Next parameter we have is downcomer backup. Okay. And all these downcomers and all that we have already discussed many times in previous classes. So we need to uh, check for this downcomer design or downcomer backup to understand that flooding should not occur. Okay. flooding will be occur when liquid passes through the downcomer and vapor moves up. Okay, so we need to consider this downcomer design. One is to uh, one is to consider the fouling and flooding, and secondly to have better vapor and liquid disengagement in downcomer, because vapor should not come to lower plate through liquid. Okay, so we need to consider this downcomer backup. So downcomer area and plate spacing. Okay, plate spacing, the space distance between two consecutive plates, right? So the downcomer area and plate spacing must be such that the level of the liquid and froth in the downcomer is well below the top of outlet wear on the plate. Okay, what is the point over here? Let me discuss it. Yes, if you see, this is if the level rises above the outlet wear, the column will flood. Okay, so what is the condition? If you consider this LT is nothing but the plate spacing. Okay, and because whatever liquid is available, it is coming from top plate, and the vapor and liquid separation occurs in this plate. Okay, and to avoid the flooding, what is the condition? The condition is whatever level of liquid is available in this downcomer, that should be well, that should be lesser than the plate spacing. Okay, if you see, this is downcomer area and plate spacing must be such that the level of the liquid and froth in downcomer is well below the top of the outlet wear on the above plate. Outlet wear means this one. Okay, it means this height should be considerably less than the this wear. Okay, and LT we are considering as tray spacing. Okay, this is one thing. So what we need to find? We need to find HB, and that I need to compare with this LT. I hope you are getting it. To find out this HB, we have different heads. Like here, you can visualize HW and HOW very clearly. HOW is the height of liquid film above the wear. Okay, like this. Okay, and HW you can see over here. And when I'm considering this particular part, like um, the space between plate and downcomer apron. Okay, what is downcomer apron? This is downcomer apron. Okay, and distance between plate and downcomer apron, that we represent by HAP. And once I'm having this HAP, we can find out this HB. Okay, so let's see how to consider that HB. Okay. So in terms of clear liquid, the downcomer backup is given by this, that is HB, which we have already seen here. Okay. HB, which is equal to HW plus HOW, that we have already seen, plus HT plus HDC. Okay, HT is the total pressure drop over the plate. Okay, and that we can consider along with HW plus HOW. Okay. Right. And plus HDC. So what these parameters are, HB is the downcomer backup measured from plate surface. Okay. HDC is the head loss in downcomer. Okay. What is the head loss in downcomer? The main resistance to flow will be caused by constriction at the downcomer outlet and head loss in the downcomer. Okay. So what is that point? That point is HDC only. And HDC, we have already discussed, that should be based on this HAP. Okay, that we will see. So HDC, how you can find this is equal to 166 LWD by rho LAM. Okay, so this is LW is the liquid flow rate in downcomer. Okay, how we can find this? Liquid volumetric flow is there, and that should be divisible by downcomer, so that you can consider over here. Okay. And AM, what is this AM? AM is either the downcomer area AD or the clearance area under the downcomer. Okay, AAP, whichever is the smaller. Okay. So here I'm having two things. One is the downcomer area, that is AD, which is usually 12% of column area. In this, actually that varies, but we consider 12% of total column area, and that is nothing but nothing but AD. Secondly, the clearance area under downcomer. Okay, clearance area under downcomer will be nothing but this area. So if I ask you how to find this area, okay, if you consider this is the uh, if you consider this HAP and area, if you would like to calculate, you need to consider the wear length. Okay, wear length of this uh, what we can say apron. Okay, sorry, the what I'm saying that wear length should be the cut part of this plate. Okay, and that LW we have already seen in the last class how to find that. And once I'm having this, we need to compare HD and HAP. Okay, HAP, how you can find out? LW into HDC, sorry, HAP. Just a moment. This area you can find out by HAP into LW. Okay, because this, it is nothing but the rectangle. So whichever is smaller, that we need to select. So AAP, we can find out HAP into LW, that we have already seen. Now how to find this HAP? Okay, if you see this schematic, if you see this if HAP is little bit lesser than LHW. Okay, HAP is lesser than LHW. Okay, and that HAP, how we can calculate that is wear height minus that how much it should be reduced. So that should be 5 to 10. Okay, and if you consider this HAP, if this HAP will be lesser, if HAP will be lesser, AAP should be less. And if it is less, it will create more pressure drop. Okay. And we need to check this HDC or HB at maximum possible pressure drop. So it is better to consider this HAP as like this should be lesser. Okay. And thus we consider HW minus 10 mm. I hope you are getting HW minus 10 AM, 10 mm. Okay. Now, once I'm having this, we can find out this HB, which you can see over here. And that the condition is that should not be more than half of LT plus HW, half of plate spacing plus HW. Because if you see here, I'm having the total distance from here to above here. Okay, it's not half of this LT. HB should not be more than half of LT plus HW. Okay, so that condition we need to satisfy. If it will not be satisfied, what we need to consider? We need to increase LT. Okay, LT means plate spacing, and when you will change the plate spacing, all calculations from column diameter will change because it will depend on if you recall the flooding velocity, it will it depends on K1 and K1 depends on the plate spacing. Okay, so you need to be very careful while choosing the parameters, or by varying the parameter, you need to repeat all calculation on which this parameter is involved with. Okay, so that you can consider. So condition is this. How to find this condition feasible, that also we have seen, and accordingly you have to change other parameters also. Now next is the downcomer residence time. Okay, that downcomer residence time is important to have the disengagement for vapor as well as liquid in downcomer section. So sufficient residence time must be allowed in downcomer for entrained vapor to disengage from liquid stream and to prevent froth being carried under the downcomer. So we should not have vapor along with the liquid in downcomer. Okay, so separation must be required, and for that separation, the mixture should stay for sufficient time in downcomer section. So therefore, that sufficient time we can call as sufficient residence time. So let's see how to find that. So that residence time will depend on AD, that is downcomer area. HBC we have seen already. Okay, HBC will be nothing but it should be HBC. Okay, rho L by capital LW. Okay. HBC, which is equal to HB, total downcomer backup. Okay, HB is the height of liquid or height of mixture over this uh, in the downcomer. So TR should be AD HBC rho L by LWD. Okay, so in this way you can find out this TR residence time, and that TR uh, should be more than 3 seconds. The condition is TR should be more than 3 seconds, right? If it is not, you need to change the column diameter. You need to change the downcomer area. And again, if you are changing this, you can have that uh, uh, column diameter calculation you need to repeat from. Okay. So condition is TR should be more than 3 seconds. Now we have one example for design of plate, and whatever method we have discussed, okay, that method should be for sieve plate. Okay, it is not for other plates. So let's see the example, and this example I have directly taken from the book Richardson Coulson volume 6. So design the plates for column located at the bottom. So we need to design the plate which is available at bottom. Okay. This location is very important. I'll tell you how to consider that. We have already discussed in previous classes, but with the example, it will be more clear to you. Okay. We need to consider the turn down ratio as 70%. Okay. Turn down ratio means the ratio of maximum to minimum feed rate. Okay, so maximum feed rate we are already given as 13,000 kg per hour, and 70% of that would be the minimum flow rate. Okay, so we need to design the sieve plate located at bottom. Different parameters we are already given, and this actually plate design will come once you have already make the mass and energy balance in distillation column. You have decided reflux, everything you have decided depending upon the operation, and then you need to proceed for single plate design. Okay, so we are already having this data. Okay, so slope of bottom operating line and top operating line, that you can consider as 5 and 0.57 respectively. Reflux ratio 1.35. Feed, it is basically 13,000 divided by this. So that should be more molecular weight. Okay, that you can see in the example. Okay, because this example, whatever I am considering, that example they have considered to calculate other parameters also, and there somewhere you will find this 19.32 as molecular weight. Okay, so in mole we can consider, then top product we are having as this 23 kilomole per hour. That you can make the balance also, right? And once I'm having this D, we can find out vapor rate, and that vapor rate below feed and vapor rate above feed. And similarly, the bottom product you can find, and and after that we can have the liquid flow rate at bottom. Okay, slopes are already given. So considering all these parameters and these properties, we consider property different at top and bottom. And because we find the variation in temperature significantly at top and bottom, right? So we observe change in density. Okay. And if you see the surface tension over here, it is 23 into 10 to the minus 3 and 57 into 10 to the minus 3. So this is more than what we can say 20 into 10 to the minus 3, which is recommended for uh, to find the design constant. Okay, that we will discuss. Okay, so let's start this example. The first step is to find out column diameter, and as I have told you that column diameter is only the parameter which does not depend on the location. Otherwise all parameters are location dependent. Okay, so column diameter you can find as FLV. uh, And this FLV you need to calculate at top and bottom, and that is nothing but L by V. So for top and bottom operating lines, these are already given. We have the densities. Okay, FLV expression we have seen in the last class. Okay, so FLV for top and bottom you can find like this. Okay, now once I'm having the FLV, we can use this graph to find out K1. Okay, and this K1 depends on the plate spacing. So to start the calculation, we can assume plate spacing as 0.5 meter, as you can see through this graph. Okay, FLV top and bottom, these are given, and zero point 0.5 somewhere the line will come in between this, and you can see the value of K1 for top and bottom both, right? So for base or bottom K1, it is 7.5 tensor minus 2. For top, it is 9 tensor minus 2. Now, once I'm having this K1, we need to correct the value. So correction for surface tension is required because the liquid surface tension is considered as 0.02 Newton per meter. And here the surface tension varies, as we have already seen. 23 and 57 into 10 to the minus 3, that we have already discussed. So K1, we need to multiply this uh, K1 by sigma by 0.02. Okay, power 0.2. So here you can see we need to consider this that row which is already given in the problem and divide by 20, because 20 is coming from here. Okay, so into this K1 and into K1 at bottom as well as top, that you can consider. Another point to consider over here, that in the problem it is not given that whole area to active area percentage is what. Okay, so that is you. Once I'm using this graph, this one, the okay, once I'm having this graph, the whole to active area percentage we have considered as 10. Okay, if it is 9%, 8%, you need to uh, multiply the correction factor for that also in K1. Okay, here it is not, it is considered as 10%. That's why it is not considered over here. Now, once I'm having this K1, we can find out flooding velocity at top and bottom, as you can see over here. Okay, so this is the flooding velocity in the distillation column. And once I'm having the flooding velocity, the actual vapor velocity should be what we can say 70 to 90% of flooding velocity. Okay. However, recommended value is 80 to 85%. So we will start with 85%. You can start with 80 also. Doesn't matter. Okay. So 85% flooding at maximum flow rate. So we need to consider 85% of this, 85% of this. So in this way, you can find out the velocity of base as well as top. Okay, now once I'm having this vapor velocity, we need to find out the vapor volumetric flow rate. Okay, so maximum volumetric flow rate is this 162.3 into 18 by 0.72. Just a moment. Yes. So this is the flow rate which we have fixed, and that is it is given in moles. Okay. So this we have to multiply with this molecular weight. Okay. And that divide by 0.72, that is density. So considering this, you can find out the volumetric flow rate at maximum condition. Okay, because if you consider the flooding condition, okay, flooding condition decides the upper limit of the vapor velocity. So we also need to consider the flow rate, um, upper flow rate of vapor. Okay, so therefore maximum is considered over here. Otherwise, here we need to consider 70% of this, okay, which we will not consider over here to have maximum volumetric flow rate, right? Net area required is that volumetric flow rate by area. Okay. So that area we have, sorry, this is the velocity, not area. This is the vapor velocity. Okay. And this is the volumetric flow as we can see over here. So bottom 0.40 meter square and top 428 meter square. And this is nothing but the net area. Okay. Net area we consider as the whole plate area apart from downcomer. Okay. So cross sectional area of the column minus downcomer area, that should be the net area. And downcomer area, how you need to consider like it may vary, but you need to start with 12%. That is, it gives the feasible outcome. Okay, so 12% downcomer area we have considered. So column area should be this divided by 0.88. Okay, column cross sectional area is this divided by 0.88. Okay, because 12% downcomer area we have already deducted. So base area will come as 0.46 meter square for yes, 0.46 meter square, and top is 0.32 meter square. So once I'm having the cross sectional area, the column area we can find depending upon the base as well as the top. Okay, so column area you can consider as 0.77 meter, which is more than this. So we will choose 0.77 as column diameter. Okay, so in this way you need to find out the diameter always depending whatever the location may be. Okay. So once I'm having the column diameter, next is parameter is or next step is to decide. Next step is to decide the liquid flow pattern. Okay, liquid flow pattern, it is required to calculate the, required to find out in which region we are falling. Okay, so it will depend on the maximum volumetric liquid rate. Okay, not the minimum one. Okay. So maximum volumetric liquid flow rate, that is L Lm prime it was given before. Okay, in the problem, if you see, it is already you can already calculate this 811.6 into 18 by this density. All that you can find out. It's not complicated to explain, but maximum volumetric flow rate you need to consider for liquid, and that you need to trace in this. Okay, so if you see 4.3 I'm having, so somewhere it will lie over here. Okay, 4.3 or something. So it is in this, and this DC is the column diameter, which is 0.77 like this. Okay, so if you see the somewhere here it will lie, so you can choose cross flow single pass. Okay, so in that way you can have the pattern of liquid. Okay, it is for single pass. And what is that single pass? That already we have discussed in the last class. Okay. Next, we need to check for the entrainment condition. Actually, what happens that just let me discuss over here. Here, 0.77 meter we have considered as the column diameter, right? So this is the calculated value. Okay. However, you can find the column diameter based on standard dia which is available. So in the book it is given as 0.77 we obtained, and 0.79 is the diameter that has been selected. If you are if you aware of standard diameters which are available in market, okay, otherwise whatever calculation you are considering, you have obtained the diameter after calculation, that you can consider as it is. Okay, but ideally it should be that diameter which is available in the market above this. Okay, therefore 0.79 we have considered, and once I'm having 0.79, okay, column diameter, the flooding percentage will also change. Okay, so here you will consider the UH, that is vapor flow, and 1.13 is the volumetric flow divided by 0.44, that is nothing but the net area. Here if you see what we have obtained, net area as 0.46. Okay, but here you can find this net area as 0.44. How we have obtained this, that we will discuss. So percentage flooding is basically the vapor flow in actual condition divided by the vapor velocity at actual condition and vapor velocity at flooding condition, that we have already calculated. So 76 would be the what we can say percentage flooding instead of 85 which we have assumed. Okay, however, if you are considering the same column diameter which you have calculated, there is no need to find out percentage flooding, that you have already assumed, and you are you are computing the parameter based on 85%. Okay, however, if this percentage flooding you are getting, okay, this you need to find out, this you need to consider to find out the entrainment. Okay, entrainment depending upon this FLV depend upon the location. Even when I'm saying this is about, this is it depends on the location. What location we are considering? Bottom plate, right? So that bottom plate, therefore L prime we have considered, otherwise we should consider L, right? And this FLV we can have for the bottom plate only, and we can see this psi value from the graph, and that should be less than 0.1. Which graph I need to consider? You can refer the last class. Okay. Yes. So it means entrainment are not that much that it will cause flooding further. Okay. So that we are already in safer side. Okay, so this is the condition for entrainment we need to check. Then we will consider the provisional parameters for design of plate. So column diameter, you see here, it has been taken as 0.79 instead of 0.77. So column area will change, then downcomer area will change, and then net area will change. So you see net area 0.44 meter square we have obtained over here, right? So once I'm having the net area, we can find out active area, which is equal to column area minus twice of downcomer area that you can see. Okay. So downcomer area 0.06, so 0.12 we have considered, and whole area to active area is 10%. So 0.038 is the whole area AH. Okay, that you can see. So these are some of the parameters which we have considered, and we need to find out the weir length. Weir length, how you can find? Weir length, when I'm considering, it depends on the downcomer. Okay, so AD, somewhere it is given like AD by AC, column dia by downcomer area by column area, or on y-axis I'm having LW by DC. Okay, that graph we have discussed in the last class, you may refer. And we need to consider the weir height as 50 mm, which is the recommended value to start with. I'm not saying this value is correct, but that initial guess you need to take. Okay, column diameter 5 mm and plate thickness 5 mm. Okay, weeping point. Next parameter we need to consider is the weeping condition. Okay, and all that parameters will be calculated for bottom plate. I don't need to repeat it again and again. You please consider this. Okay, except column dia, others should be location dependent. So here we will consider the maximum liquid rate, and this is the LW prime, it is given. Okay, so maximum liquid rate 4.06 kg per second. Okay, minimum should be 70% of that, right? 2.84, it is given. And we need to find out HOW, crest height. Okay, that is 750. Here I'm having LW by rho into that LW, weir length. Weir length we have obtained as 0.6 meter, right? So that you need to consider over here. Minimum HOW you can find as 22 mm of liquid. And minimum rate I'm having like weir height plus HOW. Okay, so that we 50 mm weir height we have already considered. So 72 mm is the minimum. What we can say, minimum height. Okay, and where this height will be used in this graph to find out this K2. Okay, just a moment. Yes. So in this way, you can find out HW and HOW, and you can see value of K2. And this K2 will be required, which is coming as 30.6. This is required to find out the vapor velocity at which flooding will occur. Sorry, at which weeping will occur. Okay. And yesterday class also we have discussed that upper limit of vapor velocity should be decided based on flooding condition, and below limit should be decided based on weeping condition. So UH you can consider as this is K2 and all parameters are given. This is whole dia. Okay, 5 mm. Okay, and all parameters, you know, this is density. So 14 meter per second is the whole, is the vapor velocity through holes at which flood, what we can say, this is the minimum velocity, right? So design velocity, what we are considering for vapor, that should be more than this. Okay. So actual vapor velocity minimum, we need to consider as minimum vapor rate by AH. Considered minimum because if condition will be satisfied at minimum condition, or minimum value, it will be satisfied at above value also. Okay, so we need to check with the minimum vapor rate only. So if you see here, I'm having vapor rate, that volumetric flow we have calculated as 1.13 for bottom. 70% of that you will consider to find minimum rate, and that is nothing but the whole area 0.038 that we have already seen in previous slides. So 20.8 meter per second is your um, minimum actual vapor velocity, and which is more than 14 meter per second. So this condition or weeping condition is satisfied. Okay, so weeping will not occur. Okay, now the point is, if this condition will not be satisfied, okay, if UH is coming more than this, what you will do? If you see, or this minimum vapor velocity, this parameter cannot be changed. Okay, because it depends on volumetric flow, which depends on the V value, and that is the fixed value for distillation column. Okay, you can consider change in AH, that is whole area, uh, as more, so that this should be, sorry, this you need to consider as lesser, so that this should be increased. Okay, so AH you can consider now as 8%, 9%, whatever, but if you are changing this, you need to reiterate from diameter calculation, because that uh, what we can say, K1 will depend on this hole to active area percentage, right? So better is to vary this. If UH is coming more than this, you need to reduce this UH. Okay. And how you can reduce this? Okay. By reducing the hole diameter. Right, by reducing the hole diameter. That is 5 mm we have taken. You can take 4 mm, up to 2.5 you can go, but not beyond 2.5. Okay, if at 2.5 also condition will not satisfy, then you should choose this. You should change, what we can say, vary this AH. Okay, otherwise not. Okay, so just try to consider those parameters which affect the design, previous design, what we can say, minimum. Okay, so once I'm having this whipping condition, we will find out the perforated area, because we need to check the whole pitch. Okay, so this is the perforated area, the, what we can say, this inner schematic. Okay, theta c that we have already discussed. 50 mm is the what we can say, calming zone um, uh, thickness, as you can see, 50 mm, and this is also 50 mm. This is basically the part of ring. Okay, part of the support ring, which is 50 mm, and 50 mm is again the calming zone area. Okay, so 0.79 is the column diameter, 0 0.6 meter is the weir length that we have already seen. Okay, so theta c you can find from here, that is LW by DC 0.6. LW is given. Okay, this LW is given like this. So we can find out theta. Okay, LW is what we can say this. Okay, this ratio we need to consider. I'm sorry. This ratio we need to consider. So LW by DC you can find as 0.76, which is coming like somewhere over here, and you can find this theta c, and that theta c will you can get as 99%. Okay, once I'm having this, we can make the that geometry, we can apply the geometry and find out the perforated area. Okay, that you can see, actually this is not very complicated, that you can observe, that you can do. So perforated area we are finding as this is the, this is what, this is active area minus the area of this calming zone, both the side, and area of this ring. Okay, both the sides. Okay, so that you can see. And a perforated area is coming as 0.262, and this AH by AP, that is, it is given as 0.145, right? And once I'm having this AH by AP, consider we need to consider either this graph or equation we have already discussed in the last class. So LP by DH is coming as 2.6, and that should be within 2.5 to 4. Okay. So in that way, you can consider, you can say that your whole pitch is also at uh, given range, feasible range. Okay, so design, so far the parameters which we have chosen for calming zone and thickness of ring, support ring and all that will be satisfactory. Now, once I'm having this, what we can say, this whole pitch, we can find out number of holes. Number of holes would be area of hole divided by the area of single hole. Okay, so that is AH by this one, area of one hole. So you can find the number of tube holes as 1935. Fine, and that all these will be available in this perforated area, not much, not in this area, coming zone area and all. Okay, just a moment. Right. So in this way, you can find out number of holes, and then we will calculate the plate pressure drop. Okay. So as we have discussed that pressure drop will be because of vapor movement and because of liquid movement. So vapor movement, we consider dry plate pressure drop, and liquid movement, we consider the head which is available over the plate. Okay. So first of all, we need to find out HD, and that HD will it includes the vapor velocity through holes. Okay, so that we need to consider, this is volumetric flow. Okay, and this whole area, because we need to consider this pressure drop, consider this UH maximum, so that we can deal with maximum pressure drop. We can calculate maximum pressure drop. Okay, plate thickness to hole diameter, that we can consider 1, and AH by AP we have already seen. And instead of AH by AP, we can consider AH by AA, active area. Okay, so you can find this, and one is there. So C naught you can find from this graph, which is coming as 0.84. Okay, and after that you can find out this HD. So you can have 48 mm water, sorry, 48 mm of liquid column. Okay, and we have residual head that it is coming as 13.1. It is not very complicated, and total pressure drop should be that HD, HR, HW, and HOW, crest height. Okay, crest height we have considered over here. Just a moment. Yes, if you consider HOW, we have taken as 22. That is for minimum. Whatever in pressure drop we will calculate, that should be for maximum. Okay, so instead of considering 2.84, we need to consider 4.06 over here. I hope you are getting my point. Okay. So it is coming as 27 instead of 22 HOW. So HT you can find as 138 mm of the liquid. So that you need to consider. Okay. And then you can find out pressure drop. Simple rule GH you need to do over here. Now, next parameter is downcomer backup. Okay, so we will consider the downcomer pressure losses, and that should be HAP. So it should be HW minus 10. Okay, 10 because HAP we need to consider as minimum. Okay, you please understand it properly, where I'm considering minimum, where I'm considering maximum. And when if you solve the problem on your own, then all these things you need to keep in mind, and then it will be more clear to you. Okay, but I hope this example will help you to understand. Okay, so area under the apron, that is AAP, that is wear length into this HAP, which is coming as 0.024 meter square. Downcomer area we have taken as 0.06, which we have already calculated before. So what we need to consider, we need to choose minimum among these two. Okay, either AAP or AD, we need to consider minimum among these two. So 0.024 we have taken, so we can find out HDC. So in that way we can consider that HDC may be that 6 mm or so. Otherwise we can take this value also, and backup in downcomer, that is HB height of liquid and froth that we need to find out. So for that we have to consider HOW plus plate frictional loss plus 6. Okay. So in this way you can find out the total height. And this total height is coming as 0.22 meter, and that should be less than half of plate spacing plus wear height. Plate spacing we have taken as a 0.5. Okay, so plus wear height by 2. So that value is coming lesser than that. So this design should be acceptable. So next parameter we need to find is the residence time. So residence time expression is given over here. You can find this LWT that we have already seen with the that maximum flow. Okay, so TR is coming as 0.06 into 0.22 into density, and it is coming as 3.1 second, which should be more than 3 seconds. So residence time is also sufficient, right? So in this way, you can find out the parameters used in design of plate column. Plate, when you are considering, that is on the very small in comparison to column diameter, but efficiently design of this plate will give efficiency to the distillation column. I hope you are getting. So we need to calculate many parameters for plate design. Okay, so it is very small, but it is quite complicated to design with. And what I'm feeling that I have tried to explain all parameters as much as I can, but this distillation column includes so many parameters in designing. Um, you may get confused, okay, where which one should be considered. Okay, so please practice the uh, problem. I will also share some of the problems with you to solve either as assignment or something. So the things will be more clear to you. Okay. Now here I'm having another example for plate hydraulic design. Okay, so in this, a distillation column is to be designed to separate a mixture of acetone water. Feed contains 4% by weight acetone, and 95% of that should be recovered uh, from top. Okay, other 5% should be at bottom. So bottom, because only 5% to 95% would be water only in bottom. Okay, so bottom product is essentially water, maximum feed rate 15,000, turnaround ratio 75%. We have certain parameters like number of real trays 18, slope of top and bottom operating line, that is given. And here I am having physical properties, okay, depending upon top and bottom temperatures. Okay, and column spacing we are given as 0.6 meter, hole to active area 8%. And here we also uh, um, can observe the uh, surface tension, okay, at top and bottom.